one and all. So this is 29th lecture in ad hoc sensor networks. So we have completed the first part of module number 5. This is the second part of module number 5. The module number 5 is called as hybrid wireless network. So in this second part, we are going to see the recent advances in wireless network. So there are mainly 3-4 technologies that we are going to check. First technology is called as ultra wideband radio communication. Next technology is called as wireless fidelity, and the last technology is called as optical wireless network. And there is IEEE 802 standard that also we will see in this. So before we are starting any of the recent advances, two things I would like to tell you. First thing, it was mentioned in the initial stage of this module 5, that is whatever recent advances they are talking, this recent advancement is from the point of view of when the book was authored. Okay, so it was authored maybe 15-20 years back. So at that time, all these technologies, that is ultra wideband, which is called UWB, then wireless fidelity Wi-Fi, and optical wireless network, then WDM, all those things were recent advances. But now, as of date, all these technologies have are not quite advances. They are very much in use, and they have, many of them have become obsolete as well. Okay, so by the time the book was written, from that point of view, these were the recent advances. Okay, so let us start with the introduction to the recent advances in wireless network. So initially what we had seen was infrastructure based network, infrastructure less network. Then we have seen many applications of ad hoc wireless network and all. And finally, in the last part of this module 5, what is explained is what are the advances in wireless network technology. So mainly there are three network technologies: ultra wideband, wireless fidelity, and optical wireless network. Out of that, we are going to check only one, that is ultra wideband radio communication in today's lecture. What is the need of this advancements? That is the first question. So in recent advances in wireless network, in introduction part, what you can see is, as per expectation, the predominant mode of internet access is all over wireless network. So you have to think 15 years back. Okay, at that time internet was quite a huge thing, so everybody started using it, but it did not come on mobile at that time that much. It was only based on laptop or PCs. Okay, so in order to support high data rates on short ranges, promising technologies such as ultra wideband transmission scheme and optical wireless wavelength division multiplexing, which is called as WDM or WWDM or ODM, all those networks were currently under use. In addition to the demands on increasing the performance of the lower layers of the system, pressure is on the efficient reuse of the existing frequencies. So frequency reuse is the main buzzword for this advanced wireless networks. So this also demands allocation of newer bands for commercial wireless communications. So frequency reuse and using different newer frequency bands, searching for them and using, this is the main technology in this advanced wireless networks. So what are the features of next generation ad hoc wireless or next generation wireless network technology that we'll see now? So in additional areas of interest in next generation wireless networks include, so these are the features. Number one, freedom in selection of particular network from a set of heterogeneous wireless networks. That means, suppose, let's say I'm using uh, 2-3 different communication range, so RF, maybe Zigbee, maybe Wi-Fi. So I should be able to switch among all these technologies. Okay, so switching from one network to another network, or like I'm using what Airtel, Geo, and Vodafone, so I should be able to switch among any network. Okay, so that is the kind of flexibility this recent advanced network should be able to give. Second is seamless handoff across such networks. So what is meant by handoff? From one network, if we are entering, if you are leaving one network and entering another network, okay, the handoff from one network to other network, they should not cut off the communication, or they should not show any glitch in the communication. So that is called seamless handoff. That means there should not be any particular problem while handing off or leaving one network and entering the other network. Number three is support for multimedia traffic. That is very important. That very high bandwidth of data traffic, voice traffic, video traffic. Okay, so if we want to transmit or receive video data, voice data, all those things, so our internet data, we should be able to do that without much problem. And last one is all the above services at an affordable cost. So cost is of prime importance. So all these things, that is switching among network, then seamless handoff across the network, then support in multimedia traffic, that is high volume of traffic. All these things should happen in a very lesser cost. Okay, in that case we can say that this is a very advanced, okay, and recent wireless network for our use. So first step in this is to develop a wireless fidelity system or Wi-Fi system. This is a full form that integrate high-speed wireless LAN with the wide area packet cellular infrastructure. So both these things are very important. That is, one is high-speed LAN and second one is wide area packet cellular infrastructure. Both these things should go together. Demand for high bandwidth or high quality multimedia traffic has also resulted in utilizing the WDM technology in wireless communication. The recent advances in the area of wireless networking, such as ultra wideband, wireless fidelity, optical wireless communication, and IEEE 802.11 ABG, are discussed under advanced wireless network here. So let us start with ultra wideband radio communication. So two major differences between ultra wideband technology and existing narrowband technology. So the two differences are explained below. First difference is the bandwidth of ultra wideband system as defined by FCC. So Federal Communication Commission is the body worldwide who are regulating all these frequencies and all. Okay, so Federal Communication Commission (FCC) they are saying that the UWB bandwidth should be more than 25% of the center frequency or bandwidth greater than 500 megahertz. So there's a very important thing. So as mentioned by FCC, the bandwidth of UWB system should be more than 25% of the center frequency or bandwidth greater than 500 megahertz. So this is the bandwidth and center frequency specification. Next difference, which is also a feature of UWB, it says that the narrowband and wideband technologies make use of RF carrier to shift the baseband signal to the center of the carrier frequency. So we know the modulation technique, but ultra wideband systems are implemented as a carrier less fashion. Very important word. Okay, so ultra wideband systems are not directly using any kind of carrier. Okay, so they are called as carrier less fashion, in which the modulation scheme directly modulates the baseband signal into an impulse with very sharp rise and fall time. So this is actually the feature of UWB, that UWB system is using a carrier less kind of modulation technique, and in this case the modulating signal modulates the baseband signal into a impulse with very sharp rise and fall time. Very sharp rise and fall time means this impulse signal used in ultra wideband is very thin in time domain. That means their time period is very small. That means the frequency is very high. So it results in waveform ranging from several gigahertz bandwidth. So as the time period of the waveform impulse are very small, it will be resulting in a gigahertz bandwidth. So this impulses have a very low duty cycle. So what is meant by very low duty cycle means on time is very low compared to the overall time period of the pulse. So definition of duty cycle is on time divided by on time plus off time. Okay, so whenever I'm saying that, so on time will be very less, and on time plus off time, there's a total time period will be more. Okay, in that case, the duty cycle will be very less. A simple example of ultra wideband transmission is any radio frequency RF transmission with 500 megahertz bandwidth and a center frequency of 2 gigahertz. So remember this, that UWB transmission is any radio frequency with 500 megahertz bandwidth as mentioned previously. So this is a bandwidth of UWB 500 megahertz and center frequency of 2 gigahertz and above. Here, another new thing we are talking about. So this is a narrowband thing. This is called IEEE 802.11a and IEEE 802.11b. Okay, so they are actually narrowband. So this is ultra wideband, and this 802.11a and b, they are called as narrowband. So this difference is asked. And what is the difference between ultra wideband and narrowband technology? So IEEE 802.11b, which is a narrowband system, it is having 22 megahertz bandwidth and center frequencies ranging from 2.412 gigahertz to 2.462 gigahertz. Okay, so there's a difference between narrowband and wideband. So ultra wideband is having bandwidth of 500 megahertz and center frequency of 2 gigahertz, whereas the narrowband wireless frequency is having bandwidth of 22 megahertz. So just check, this 22 megahertz for narrowband is becoming 500 megahertz in case of wideband. Okay, and center frequencies ranging from 2.412 to 2.462 gigahertz in case of narrowband, but in case of ultra wideband it is 2 gigahertz. So center frequencies are quite comparable, but bandwidth in case of ultra wideband is very high. Okay, that is almost how much? Almost 20 times or more than that. Okay, so just check. Principles of ultra wideband technology. So actually we are trying to find out what are the advantages that ultra wideband technology is offering, and why are we calling it as a recent or advanced technology. That is what we are trying to find out. Okay, so the principles of ultra wideband technology had been applied in radar application since 1980s. With proper emission restrictions on the upper limit on the transmission power, the ultra wideband spectrum can overlay the existing narrowband spectrum, resulting in much more efficient use of existing radio spectrum. So what is being found is, because ultra wideband is having a very wide bandwidth, okay, so this ultra wideband will be able to exploit all the advantages of narrowband spectrum, and ultra wideband will be performing a lot better than the narrowband spectrum. So now this diagram is very important. If asked the difference between narrowband and ultra wideband, you have to draw this diagram, and this diagram and next diagram. So next these two, these are going to give you the frequency related information of ultra wideband spectrum. So here you can see there are one. Okay, so this first one is IEEE 802.11b band. Okay, so this is a narrow band. Okay, and these three are called as 802.811a band. Okay, so this is also narrow band. This is also narrow band. So these are the frequencies used for communication. And down, whatever we are seeing is from 3.1 gigahertz up to 10.6 gigahertz. This is called as ultra wideband. Okay, so narrowband B is 2.4 gigahertz to 2.5 gigahertz. This is IEEE 802.11b. This is the narrowband B. Narrowband A is IEEE 802.11a bands. So actually IEEE 802.11a is having three bands. First band is ranging from 5.15 to 5.25 gigahertz. It is written here. So this is the first band, which is ranging from 5.25 to 5.35 gigahertz. Second band 5.15 to 5.25 gigahertz, and third band is between this one. So third band is 100 megahertz. So these are the three bands. So here it is written that upper limits of transmission power permitted for the ultra wideband system are compared with 802.11a and 802.11b are shown here. So this three are 802.11a. In that we are finding three bands. One is 5.15 to 5.25 gigahertz, and there is 5.25 to 5.35 gigahertz. Another one is the last one. This is 5.725 up to 5.825. Actually, 100 megahertz is the bandwidth. Okay, and the band is ranging from 5.725 to 5.825 gigahertz. This is 5.15 to 5.25 gigahertz. That means how much megahertz? This is also zero point 0.1 gigahertz. Zero point 0.1 gigahertz means 100 megahertz. Likewise. Okay, so all these three bands within 802.11a, they are 100 megahertz wide, but the first band, okay, and second band and third band, they are having different EIRP. So EIRP is a term that we will know. Okay. So what are the things to be understood from this diagram, and you have to write all this details. So first one is ultra wide band. It is ranging from 3.1 gigahertz to 10.6 gigahertz. The width is 7.5 gigahertz. This is the first thing. Narrowband B 802.11b. This is from 2.4 to 2.5 gigahertz, and narrowband A. This is having three bands. First band is 5.15 to 5.25. Next is 5.25 to 5.35, and next one is 5.785 to 5.825 gigahertz. Upper limits of transmission power permitted for the ultra-wideband system compared with IEEE 802.11a and IEEE 802.11b are shown here. So power comparison for each band, they are shown here. It is something mentioned here: 24 dBm, 36 dBm, 16 dBm. These are called as EIRP. Okay, so what is EIRP? We will see just now. Okay, So this first thing that is 802.11b band, this is having the EIRP of 36 dBm. Okay. And this is having power spectral density that is 16 dBm per megahertz. So let us see. The 802.11a standard has three bands, each with 100 megahertz bandwidth. So I told you before, 5.15 to 5.25 100 megahertz, 5.25 to 35 100 megahertz, and this is also a 100 megahertz band, which is from 5.725 to 5.825. And the upper limit of effective isotropically radiated power. So this is actually the full form of EIRP. Please prepare this. This can be asked in the short question. What is meant by EIRP? Definition is given in the next slide. So this is a power. Okay, so this is effective isotropically radiated power. Isotropically means in all directions. Okay, so these channels are radiating how much power in all directions, that is given by EIRP. So more is the EIRP, better is the transmission. Okay. So first, this channel that is 802.11a, the lowest band is having EIRP of 16 dBm. Okay. Second one is having EIRP of 24 dBm, and the last one is having EIRP of 30 dBm. That means this channel power is highest. You can check. The second channel power is medium, and first channel power is lowest. And this 802.11b is having highest EIRP. That is nothing but 36 dBm. Comparatively, you are finding the UWB, that is ultra wideband dBm, is very less. EIRP is very less. How much is it? Is minus 41.3 dBm per megahertz. Actually, this is power spectral density we are finding. So dBm is not mentioned, but yes, dBm in this case is also very low. Okay, because if this becomes 16, that means this becomes very less. So EIRP for UWB is very less. We can find that. So it is written here that the effective isotropically radiated power is 16 dBm, 24 dBm, and 30 dBm for upper bandwidth frequency range of 5.72. So these three ERPs are explained. This ERP is explained. So all these details you have to produce if this is asked in the exam. And what is the ERP of UWB? It is very less. Okay. And next slide, another thing. So this mainly you have to understand and remember the details and specifications of every channel. Okay. This results in power spectral density. So now there's another term which is given by this minus 3 dBm per megahertz. Okay, so minus 3 dBm per megahertz is nothing but the power spectral density. That means every frequency component, how much power is there in every frequency component within the bandwidth, that is given by power spectral density. Okay, so power spectral density for this 802.11a, lowest one is minus 3 dBm, the mid one is 4 dBm, and the highest one is 10 dBm per megahertz. That is per megahertz bandwidth in case of 802.11a, that is carrying 10 dBm of power. That is what is meant by power spectral density. Okay, so this one is minus 3, this one is 4, and this one is 10 dBm respectively. Whereas this 802.11b, it is having power spectral density very high, that means 16 dBm per megahertz. So one thing you can understand is more is the EIRP, more will be the power spectral density. Okay, so this thing UWB ultra wideband, they are having very less EIRP because the peak is less, that means power is less, and they are having very less power spectral density as well. That means every frequency component, in this case every megahertz, is carrying very less amount of power in case of this yeah, ultra wideband. Okay, so that is how much value is minus 41.3 dBm. Okay, so this figures you have to remember. So power spectral density is how much, and dBm EIRP power is how much. So both these things you have to understand. So after that, what it is saying that ultra wideband systems to be power spectral density minus 41.3 dBm per megahertz, as shown in figure, ultra wideband signal appears as noise to systems that utilize the same spectrum. So all this 802.11 A and B, they are having very high power. That means they are very much looking like a signal, whereas this is very less power. EIRP is very less, power spectral density is very less, and this might look like noise signal whenever compared to IEEE 802.11 band. So this is what is said here, that ultra wideband signal appears as kind of noise to the actual 802.11a and 11b signals. What is EIRP? So EIRP of a transmission system is in given direction is the transmission power that would be needed with an isotropic. Isotropic means omnidirectional, in all the directions, radiator to produce the same power density in the given direction. Okay, so this is the definition of EIRP. That is, EIRP of a transmission system in a given direction, that means for any direction, is the transmission power that will be needed with an isotropic radiator to produce the same power density in the given direction. Okay. So this is all about the specifications of ultra wideband spectrum compared to 802.11a and 802.11b. So 802.11a and b, as you can see here, there are four bands. Each band is very narrow. Okay, how much is the width of each band? 100 megahertz. So there are four bands, three in 802.11a, they are all narrow band. There is one band that is 802.11b. Okay, this is also narrow band, but ultra wide band is quite wide. Okay, so ultra wide band is having 7.5 gigahertz, whereas all other things are having very narrow band likewise. So these are the specifications of UWB and narrowband. Now let us find out how the operation, what is the operation of UWB system. So you can find here, so in the previous slide we have explained that it's having very narrow pulse width. So these are the waveforms, modulated waveform of ultra wideband. In this case, you can just find out how narrow they are. Okay, what is the width of this? This is zero point 0.5 nanoseconds. So this is the width of the ultra wideband frequency pulses. Okay, and one monocycle pulse train. So one, two, three, four thing. So likewise, all these pulses are there. They are the waveform of ultra wideband. Okay, and they are using actually PPM, that is pulse position modulation. They are using, and this is the bandwidth of the monocycle. So whenever you are talking about this signal, this is in time domain, it's written here, time in nanosecond. Width of the pulse is zero point 0.5 nanoseconds. So if you are converting that thing into frequency, then you find it in gigahertz. So in gigahertz, it is somewhat like a this kind of a frequency which is called as a band pass filter kind of a response. Okay, and between these 2 point is the bandwidth of the whole system, because these two are the between the 3 dB frequencies likewise. Okay, so the operation of ultra wideband system, this slide you have to explain. So this is one pulse width, this is monopulse cycle of zero point 0.5 nanosecond, this is monopulse train. That means every pulse is having width of zero point 0.5 nanosecond. So here almost 20 sorry 2 nanosecond time width is shown, because one pulse is zero point 0.4 means four pulses around 2 nanosecond likewise. Okay. And this is the frequency domain response of one pulse. Okay, as this is 0.5 nanosecond, this bandwidth will be quite high, and this bandwidth will be around in gigahertz. And dB power, so how much is the maximum dB power we are finding? It is minus 3 dB that we are finding. Operation of ultra wideband system is based on transmission of ultra short pulses. So that is the ultra short pulse with duration of zero point 0.5 nanosecond, that yields a wide bandwidth signal. So less is the width of the pulse, more will be the bandwidth. So which are also called as monocycles. So these are also called as monocycles. Each monocycle is similar to a single cycle of an ultra high frequency sine wave and is a single ultra short pulse. Okay, so this is looking somewhat like a sinusoidal waveform, inverted sinusoidal. As they're very narrow, there is a little bit of distortion, and width of the pulse is zero point 0.5 nanosecond. Pulse width of the monocycles range from zero point 0.1 to 1.6 nanosecond with pulse to pulse intervals between 25 to 1000 nanoseconds. So this is 0.5 second nano, 0.5 nanosecond we are showing here, but in case of ultra wideband we are finding this monopulses width ranging from zero point 0.1 to 1.6 nanosecond. So zero point 0.1 nanosecond is a further high frequency signal, 1.6 nanosecond is a low frequency signal. Okay. And it's between 25 to 1000 nanosecond. A single monocycle of width zero point 0.5 nanosecond is shown here in the figure. Figure shows a pulse train involving a sequence of monocycles generated at regular intervals. Monocycles are inherently wide bandwidth signals. The time domain function of a Gaussian monocycle, any sharp pulse whose time domain behavior can be represented the first derivative of Gaussian distribution. So PPM is used for signal modulation here. So initially they were talking that this ultra wideband is using a carrier-less fashion. Okay, and here the actual modulating signal is directly modulating the carrier signal, but carrier is not there because they are using ppm kind of a modulation scheme here. Okay. So this is comparison of ultra wideband with other systems. So you are finding actually the comparison of the four bands. So four band means it's not very clear here, but I'll tell you what it is. So this is the first comparison of range of communication. So first thing is 802.11b, that is, this is the 802.11b. This is the first thing, which is very narrow. Okay. And then there is Bluetooth. So for Bluetooth we are finding that communication range is very less in 10 meter, whereas 802.11b is having a communication range of 100 meter. Okay, so 802.11b is having very high communication range. Please understand all these three graphs very clearly, because a comparison related question can be asked in the exam. Okay, so 802.11b is having very big communication range around 100 meter. Bluetooth is having very small communication range around 10 meter. 802.11a. Okay, so what is 802.11a? In this one, which is ranging from 5.15 gigahertz to 5.825 gigahertz. This thing is having communication range of 50 meter around, and ultra wideband. So communication range of ultra wideband is also very less. This is having 10 meter communication range. So what is the advantage of ultra wideband that we can find here? Okay, ultra wideband is having the bandwidth very high. How much is the ultra wideband bandwidth and how much is the bandwidth here? We find here it is around 50 mbps, whereas 802.11a is having bandwidth of 54 mbps. This one, Bluetooth is having very less bandwidth, around 1 Mbps, so data rate is very less, and 802.11b is having bandwidth of 11 Mbps. So here ultra wideband is giving very less communication range, that is almost around 10 meter, but bandwidth. So how much data it can carry? It can carry a lot of data for short range communication. So if you're having some application that huge amount of data has to be conducted within a short range of operation of 10 meter, then we can use ultra wideband. So this is the understanding we develop from here. So there's a second type of comparison between the four things: 802.11b, Bluetooth, 802.11a, and ultra wideband. So is having highest communication range. 802.11b is having highest communication range. Who is having highest bandwidth? 802.11a is having highest bandwidth. Who is having lowest communication range? So UWB and Bluetooth both are having lowest communication range. But here, this is the third graph, and this is the best graph, which is called as capacity comparison. That how much capacity. What is the definition of capacity? This is bits per second per square meter. Okay, so this is the capacity of the ultra wideband channel. So how many bits it can carry per second for per square meter area. That is exemplary high in case of ultra wideband. This is almost 955 kbps per square meter, and this capacity is very low in case of 802.11b. It is less in case of Bluetooth. So all the things are very less in case of Bluetooth. Okay, and 802.11a, it is around 83. So capacity, that is 955 kbps per square meter. So per square meter, how much is the data that can be carried? So in that case, ultra wideband is giving you too much of advantage. Okay, so ultra wideband is having two advantage and one shortcoming. So advantages are huge capacity, 955 kbps per meter. Advantages, very wide bandwidth, that is around 50 mbps, but range in ultra wideband is comparatively less. Okay. Whereas 802.11b is having higher range, but less bandwidth and very less capacity. Okay. 802.11a is having highest bandwidth, but less capacity and less range, but okay, it's comparable. Okay, likewise. So these three graphs you have to understand, and you have to show in the exam if they are asked. There is comparison of ultra wideband with other systems. So performance of ultra wideband is compared with Bluetooth 802.11a and 802.11b. Next is major issues in ultra wideband system. What are the major issues in ultra wideband system? We will see here. Issues means you can say limitation or drawback. So with the evolution of wireless networks with higher data rates, Similar advancement in all the layers of protocol stack is required to make use of the high data rates provided by the physical layer. So we are always expecting high data rate from physical layer. The increasing application space for multimedia communications puts additional requirements on latency and delay performances. The error-prone and time-varying nature of wireless link results in large delay variation, misordering of packet. Here, the major issues at the physical and MAC layer are discussed. Issues in physical layer. So, whenever we are having UWB system, what are the issues in physical layer? What are the issues in MAC layer? That we are going to see. With the evolution of wireless network with higher data rates, similar advancements in protocol stack, similar advancements in MAC layer or physical layer are expected. So increasing application space for multimedia communication puts additional requirement on delay performance and latency. Error prone and time varying nature of wireless links results in large delay, large variation, misordering of packet. So the issues related to UWB communication when I'm talking about physical layer. So if UWB system is used, then what might be the problems in case of physical layer that are discussed here. So the wideband receiver used for the ultra wideband system, we have found out how much is the bandwidth. So bandwidth is starting from 3.1 gigahertz and it is going up to 10.6 gigahertz. So bandwidth of UWB is almost 7.5 gigahertz. The wideband receiver used for UWB system is susceptible to being jammed by the traditional narrowband and operates within the UWB passband. Okay, so generally the ultra wideband systems are using very huge bandwidth, but narrowband systems are using very narrow bandwidth. So there is a possibility that the compatibility, if you are trying to establish between ultra wideband and narrowband, there's a possibility that the traditional narrowband things will get jammed if we are trying to use ultra wideband over it. Issues such as wide bandwidth required for the filters and antenna subsystems and filter matching accuracy are major physical issues difficult to solve without adding to the cost of the physical layer interface. That means we are supposed to design special kind of ultra wideband system, special kind of antenna, special kind of filter, special kind of all other electronics for ultra wideband system. So the system which are using narrowband, we cannot use ultra wideband over that, because if we are trying to use ultra wideband over narrowband hardware, narrowband will get jammed. Secondly, if we are trying to use the ultra wideband with narrowband hardware, not possible, because for ultra wideband, what we want is special kind of filters, special kind of antenna subsystems, and all, and this will add to the cost of the overall system. At the receiver, the accurate timing is required for detecting the modulated narrow pulses accurately. So the narrow pulses means it is 5 nanoseconds. So these are very narrow pulses. Okay, this kind of narrow pulses are not getting created in case of 802.11a or 11b, but ultra wideband pulses are very narrow. Okay, so at the receiver, accurate timing is required for detecting the modulated narrow pulses accurately. So as the pulse width is very narrow, zero point 0.5 nanosecond, little bit here and there, and we are losing the accuracy of the ultra wideband system. So timing accuracy of the ultra wideband system has to be very high. That is the main point. In addition to all above, the noise from the onboard microcontroller can also result in interference that cannot be easily solved using traditional mechanisms such as bandpass filter due to the wide bandwidth of the system. What we are finding is the amplitude of the ultra wideband system is very less. Okay, and noises here, if created, they will also be in this frequency range, and that noise frequency and ultra wideband frequency will get mixed. That's why it is said that the noise from the onboard microcontroller can also result in interference that cannot be easily solved. That means the ultra wideband frequency and the noise frequency cannot be separated. Okay, so that can be the problem that cannot be easily solved using traditional mechanisms such as band pass filter due to the wide bandwidth of the system, because bandwidth of ultra wideband is quite high. Even if some noise frequency is created, that will fall in the bandwidth of the UWB. Okay, so extracting the signal energy from the noise energy in case of UWB will be very difficult. So these are the issues in the physical layer. So first issue is jamming of a narrowband network. Second issue is we have to install some new hardware in case of ultra wideband system. Third thing is the timing accuracy of ultra wideband system has to be very high, because we are dealing with very small time signal of 0.95 nanosecond or something. And fourth problem is the noise from the onboard microcontroller or something. They are getting mixed with the ultra wideband signal, and they are falling in the same bandwidth. Hence, filtering out ultra wideband signals from the noise signal might be a little difficult. Major issues in ultra wideband system in MAC layer. So that previous thing, it was physical layer, now it is MAC layer. The most important issue in the design of MAC layer protocol for ultra wideband system are: number one, controlling the channel access. So which channels to be given access for ultra wideband frequency communication is a issue in case of MAC layer. So this is major issues if we want to use ultra wideband in MAC layer. The first one is controlling the channel access. Second one is maintaining quality of service. The quality of service in this case mainly related to time, because timing in ultra wideband is the pulses are very small, 0.5 nanosecond. So little bit of time mismatch, in that case it will produce huge timing error in case of ultra wideband channel. Okay, if they are using in the MAC layer. Okay, so maintaining QoS, mainly timing QoS, is a very big problem in case of UWB MAC layer, and providing security. Okay, so providing security, controlling the channel access, and maintaining the QoS. These three are the main problem if UWB is used in case of MAC layer. So in addition to this, the design of MAC protocols for ultra wideband system is dictated by other properties of UWB. Okay, so it is not only the properties we have discussed, frequency and bandwidth. There are certain other properties of ultra wideband who are dictating that how the MAC protocols should be designed or defined for them. For example, ultra wideband systems have unique features such as precise timing or position information. I told you before that the time width is zero point 0.5 nanosecond. That means little bit here and there, and you will be losing the time accuracy. Hence, for ultra wideband, unique feature, very precise timing or positioning is required for ultra wideband. Little bit here and there, little bit delay, little bit jitter, and ultra wideband communication will be affected. Position information can be obtained by the following feature. A 10 gigahertz ultra wideband system can distinguish signal echoes. Okay, so signal echo refers to the multipath signal that arrive at the receiver through different path with corresponding delays. So whenever from some source some data is transmitted by ultra wideband, that might come to the receiver by 4 or 5 different paths, which are called as multipath. Okay, so if these signals are reaching at the receiver with a delay of 100 picoseconds, then at the receiver side we get a very scrambled kind of a signal. Okay, generally it should not happen that if through multipath the different signals, the same signal, okay, are coming at the receiver at different times with some kind of delay in between, but we can reconstruct the signal at the receiver side. But if ultra wideband is used, 10 gigahertz ultra wideband system is used, in that case they might come to the receiver at 100 picoseconds, and 100 picosecond is quite a big time for ultra wideband. So in that case that might create some kind of problem. By analyzing the different signal echoes that take different delays, a nearly exact position and time information can be obtained in general case. For a 10 gigahertz system, the delay difference could be in order of 100 picoseconds, and hence an accuracy of 3 centimeter in distance estimation can be achieved. That means from the timing, that when the signal was transmitted and when the signal is received, from this time delay we can estimate the distance of the source. But in this case, as timing pulses are having very narrow width, that's why what we are finding, there is a 3 centimeter of distance measuring delay that might happen in case of ultra wideband. Utilization of this feature at the MAC layer can improve performance of multimedia unicast and multicast communication. Okay, MAC protocol can also benefit from the flexibility of trading off the throughput with respect to the transmission range. So there can always be a business. Okay, that is how much output we want, and how much transmission range we want. If we want higher transmission range, in that case output will be less. If we want higher output, in that case you have to reduce the transmission range. So very important line this one. MAC protocol can also benefit from the flexibility of trading off between the output, that is a throughput, with respect to the transmission range. That means if we want higher output, our transmission range has to be compromised, it has to be reduced. And if we want a higher transmission range, in that case the output will be reduced. Peak amplitude of pulses and the pulse repetition frequency, which is called as PRF, can be varied to obtain constant average power. Using this mechanism, MAC protocol can provide different data rates and transmission ranges on a peer-to-peer link packet basis. Ultra-wideband system can be implemented using spread spectrum technology. You already know that, in order to provide better coexistence with the existing system. So by using spread spectrum technology, this ultra-wideband can stay for application with the other existing system. So what are the other existing system we are finding here? That is 802.11b, 802.11a, etc. Okay. So ultra-wideband system can be implemented using spread spectrum technology in order to provide better coexistence with the existing system. Above all, another major aspect of the design of MAC protocol for ultra-wideband system is the compatibility and coexistence of ultra-wideband system with existing WPAN and WLAN. So this ultra-wideband can be used with in WPAN and WLAN. Okay, so these are the applications WPAN and WLAN of ultra wideband technology, and these are some of the issues. There is the channel access control, QoS maintenance, and security. These are some issues of ultra wideband in MAC layer. So question can be asked in ultra wideband. First question is, what are the difference between narrowband and ultra wideband? So in that case, you have to tell these two things, that how much is the bandwidth, how much is the central frequency, and what is the main feature of ultra wideband, that we are using a carrier-less communication thing, and in this case, the impulse is automatically directly modulated by the modulating signal. So in ultra wideband, it is giving a frequency bandwidth almost of 7.5 gigahertz and all. Okay. This paragraph is very important because here it is giving the central frequency of narrowband. IEEE 802.11b is the narrowband, and the upper one green is written in ultra wideband, which is 500 megahertz bandwidth at carrier frequency of 2 gigahertz. Then the principle of ultra wideband technology had fallen, where you are finding its application, and ultra wideband technology can overlay existing narrowband spectrum, resulting in much more efficient use of existing spread spectrum. Then this diagram is the main difference between ultra wideband and narrowband system. So narrowband system are also having two spectrums, 802.11b, which is very high power and high power spectral density and high EIRP. This is 802.11a, which is having comparatively low EIRP and comparatively low power spectral density. But we are finding here that is the ultra wideband, which is very wide in bandwidth, almost 7.5 gigahertz, but this is having very low EIRP and very low power spectral density. What is EIRP? You can find from here in the next slide. This purple thing below is the definition of EIRP. Okay, so just find out how much is the power spectral density and how much is the EIRP for every channel in case of narrowband wireless transmissions. Then comes this is a very important thing. If operation of UWB is asked, you have to explain this very narrow frequency pulse, which is zero point 0.5 nanosecond, little bit kind of sinusoidal waveform, and this is the monopulse cycle train modulated waveform, and this is the power spectrum or bandwidth of the, not power spectrum, sorry, this is the bandwidth of the monopulse. So as monopulse is very small time, in time 0.5 nanosecond, bandwidth goes into gigahertz, that we are finding. Then there's the most important slide in case of this lecture. So the comparison of performance between Bluetooth, ultra wideband, and narrowband 802.11a and 802.11b. We are finding that ultra wideband is having highest capacity, that is 955 kbps per square meter. Ultra wideband is having almost highest bandwidth, that is 50 mbps, but range is a problem for ultra wideband. Range is very less, it is around 50 meters. Okay, whereas 802.11b is having highest range, that is around 100 meter, and capacity and bandwidth of 802.11b and Bluetooth are very less.